Hi everyone and welcome to this lecture. So in our past lectures we only saw how to deal with first order and second order differential equations, and today we are going to see how we can deal with coupled differential equations. So what is a coupled differential equation? That's the first question we ask, and let's try to answer that question by taking an example. We are going to consider an epidemic model that is a very famous model, and it's called the SIR model. So let's say you have a given population S of t. So let's say a given population S of t, and the number of individuals susceptible to this disease but yet not infected. This is the S. So these are called the susceptible cases. That means they might get infected, but it's not confirmed whether they have been infected or not. So we call them susceptible. And then there is this infected people. If you call them I of t, that means the number of people got infected, which is a function of time. These are the infected people, and then there are people who are removed or recovered. They are denoted with R of t. So this remove or recovered, that means this R can carry the number of people recovered or the number of people dying, both of them. It contains the information of these both sectors. So if someone wants to model an epidemic using these three informations, one will get the following differential equations. One will have ds by dt is equals to minus alpha I plus is, and there is this gamma r. I'll tell you what alpha and gamma means in a second. Similarly, one will have another differential equation for the infection rate, that is di by dt as alpha is minus beta I, and finally one will have another differential equation dr by dt as beta I minus gamma r. Now this is an example of a coupled first order differential equation. Why they are coupled? Because you can see that this ds by dt, that means this equation, let's call it the equation number 1, let's call it equation number 2, and let's call it equation number 3. All of this contains some variable which is a function of time, that is t, the independent variable, and there is another equation for that as well. That means if someone wants to solve this ds by dt and solve for s, one also needs to find solution for this I and this r. So this I and r are also expressed via two differential equations, and these are also related with s. So each of these variable, that means s, I, r, they are coupled with each other. So this is what a coupled differential equation is, and this type of equations arise when you want to model system, that is physical systems. Another example could be, let's say you have a spring over here and there is a mass denoted by small m. However, there is another string and it contains a ball of mass capital M. And what you can do right now is that you can pull up this mass, let's say up to x distance, and release the whole thing. So this system will contain a second order coupled differential equation. How, you may ask? It's pretty easy to see if you just write down the Newton's laws, and a very schematic way to see this is that if you want to solve for the position as a function of time for small m and capital M, you will need two coordinates, and these two are related with each other. So this is another example of coupled differential equation. A very famous example, if you are familiar with classical mechanics, is that there is this coupled pendulum. These two pendulum are coupled by some spring of spring constant k, and the solution of these two pendulums as a function of time, let's call one of the coordinates to be theta 1, another one is theta 2. So if you want to find theta 1 and theta 2, you will see that they are coupled. They are coupled differential equations. So these two examples contain the second order coupled differential equations, but for this course we will only restrict ourselves in the discussion of the first order coupled differential equations. And these coupled differential equations are also known as system of differential equations. So without further ado, now let us see an example. So we are also calling it system of differential equations. And now we want to see an example. So for our example, let us choose something very simple. That is, let's have two variables. One is x1, another one is x2. So dx1 dt, let's denote this as x1 prime. dx2 dt, let's denote this with x2 prime. And the coupled differential equations are just x1 prime is equals to x1 plus x2, and x2 prime is just 4x1 plus 4x2. Now, how can we solve this? That's our question. So what we can do, and in this video we are going to only see the informal method. So this is a informal method, not the formal method that we are going to discuss in the next video. So what you can do is that since you have an expression for x2 prime, you can take let's call this equation A and equation B for our convenience. So since you have this x2 prime in terms of x1 and x2, and you have a x1 prime over here, and what you can do is that you can take the first another derivative of equation A. So differentiating equation A with respect to t, that will give me x1 double prime is equals to x1 prime plus x2 prime, right? And x1 prime, as you can see from equation A, is that simply x1 plus x2, right? But do we need to write that over here? That's the question we are going to ask ourselves, that do we actually need to write it over here? The answer is yes. How and why will be very clear after I write this x2 prime thing. So we have this x2 prime as 4x1 and x2, right? So this will be just 4x1 plus 4x2. So this is turning out to be 5 of x1 plus x2. But still we are not decoupling the x2 from x1, because you can see that this has x1 on the left hand side, that is the second derivative, but on the right hand side there is still this x2 guy, right? So how can we get rid of that? It's pretty simple. You just take a look at equation 1, and if you solve for x2, that is equation A, sorry. So from equation A, you can easily see that this x2 is simply x1 prime minus x1, and now you can put this over here. So x1 plus x1 prime minus x1, right? All right. Oh yeah, I made a mistake. I'm sorry about that. There shouldn't be a 4 over here. Sorry, my mistake. Because it was 4x1 time plus x2, so it shouldn't be 5. Let me just rewrite this whole thing. So this is just 5x1 plus 2x2, and then we are going to use this thing So this is 5x1 plus 2 x1 prime minus x1. So ultimately we have 3x1 plus 2 x1 prime, and this was equals to x1 double prime. Now we have an equation that is a differential equation written in terms of x1 only. So our differential equation is x1 double prime minus 3x1 minus 3x1 minus 2x1 prime equals to 0. And this is something you are already familiar with, and you can easily solve it. And similarly, that is a similar calculation can be done for x2, and you can also extract out x2 as well. So this seems pretty easy, but is it always true? Let's say instead of having two equations, now you have something like a system like the following. Let's say this one is x1 prime, which is a function of time. Obviously, let's not make it explicit. It's understood from the context. And let's say this is expressed as p1t, which is a function of time, x2, p2t, x3, and so on, pn, x of n. And there is another function, and this is the non-homogeneous term. And similarly for x2 prime, this will be p1. Obviously there can be also be a p0, let's say p0 x1 term like this. So let me just write the full general thing. That wasn't pretty general. So this x1 prime is just p1 x1. Obviously these p's are functions of time, that means p of t. Let's say pi, this is an index. So you will have p2 x2 plus dot 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 plus pn x of n. Similarly x2 prime will be just p1 x1, or let's say you can have q1 x1, q2 x2, dot 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 qn xn, and so on. And let's say this goes up to x of n. And let's say here you have some n underscore 1 x1, n underscore 2 x2, dot 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 dot, plus n underscore n xn. So if you have a system like this substitution method won't work. I mean, it will take a very, very, very long time to do that. Even if in the case of three variables, it takes a long time and it becomes really complicated. So now we ask, is there any formal method to solve it? Solve this system. The answer is yes. And if you see this system over here, that is this one, you can think of it as a column vector on the left hand side where you have these derivative things clumped up, and here you will have a matrix that will consist of p1, p2, dot 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 pn, q1, q2, dot 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 qn, and so on. And finally here you will have this x1, x2, x3, dot 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 dot. And this can be written in a compact notation with this: x prime is equals to a x. And this is familiar to you from linear algebra, and we will see how we can solve this in the next video. That is, here this capital X prime is a column vector consisting of all the all the variables derivative. That's what this is consisting. That is this one. A is similar to a coefficient matrix. However, the coefficients might be general functions that depend on the independent variables, and this x is just the just the variable, that is this x1, x2 and x3. And in the next video we are going to see how we can solve this. Thank you.